Exercise 6, you have to be numbers 8 and 9. I called in, I think, every single angle there, but you didn't actually have to work all of them out.
Just finish. Just didn't have into the theories.
No.
Yeah.
Okay, guys, so for 8.1, they asked you to prove that AOBC, so this shape over here is a kite. All right, now the basic, you could just use the basic, what's the word that I'm looking for now, property, or the main property of a kite, which is that both pairs of adjacent sides are equal. All right, so adjacent means sides next to each other, so it's not the opposite sides like with a parallelogram. So for AOBC, right, that's what we're looking at. Those two sides are definitely equal because they're both radii. Do we agree with that? Right, AO is equal to BO because of radii. And then to prove that these two sides are equal, guys, there are two tangents that come from a common point outside of the circle. All right, and we learned that tangents from a common point outside the circle are equal in length. So AC is equal to BC, tangents from common point. So there you have, both pairs of adjacent sides are equal. So AOBC is a kite, and then that is just your reason. So you're basically just writing the property out that you've proved. Any questions on that first one? Okay, then the second one is quite an interesting proof, all right, and I don't know if many of you would have thought to do that because we haven't really practiced with that much. Now they asked you for the same shape, so again, this picture or this figure there, sure, I'm losing my words, that figure there, AOBC, they now want you to prove that it's a cyclic quad. Now guys, here we have a radius, AO is a radius, and there we have a tangent. And what do we know about a radius and a tangent? They are always perpendicular. Remember, tangent perpendicular to radius. So that angle there, angle A2 and A3, I just wrote OAC for that angle. That angle is definitely 90 degrees because it's a radius and a tangent. And then we have the same thing happening here. We also have that radius OB and that tangent BC. So that is again a 90-degree angle there. And those two are opposite angles of this quad. So if it's 90 and 90, then they are supplementary. They add up to 180. Okay, I don't know if you guys would have thought to do it in that way. So I just wrote that they are both equal to 90 degrees because of tangent perpendicular to radius. So therefore, OAC plus OBC is 180. So therefore, it's a cyclic quad. And remember, when you are proving that something is a cyclic quad, you write converse in front. Yes. Yes, yeah, you'll lose that. You'll lose the reason mark. Okay, then all fine with that one, with 8.2. Okay, then for 8.3, they asked you to find various angles. Now you might have had other reasons here. You can just ask me and then I'll check if it's fine. But the first one that they asked you to find was PAQ. PAQ. And guys, it actually took me so long. I tried to do like lots of other reasons. And then at the end, I was like, hello, it's a diameter, PQ. I don't know if other people had that same experience. PQ is actually a diameter, and a diameter always obtains a 90-degree angle. All right, so that one I didn't draw it in because I thought it might be a bit confusing, but that is the angle that we're looking at there. A1 and A2 together, that's PAQ, and PQ is a diameter, so it obtains a 90-degree angle. You could have found it in other ways by doing angle sum and triangle and all sorts of stuff, which also would have been fine, but it was actually just a one-liner. Then they asked for O2, which is that angle over there. Now, this is the only angle that was actually given, right? This angle at P. Do we see that this angle at P, the 30-degree angle, is subtended by AQ at the circumference? And AQ then also subtends O2 at the center. So O2 should be double the one at the circumference. All right, so O2 is 60 because P was 30. So those were the first two angles that they asked us to find there. All right, then for the other two, I did an in-between step. It might have been possible to do it without an in-between step, but yeah, you can tell me if you did it like that. So the next one they asked for was ACB, which is this whole angle over there, right? So what I did was, I did angle, sum, and triangle in this one over here because we had 60 and we had 90. So then that angle will be 30, right? In that top triangle there. Sorry, the picture is very busy, so I apologize if you are struggling to make sense out of this. So C1 I calculated is 30 degrees. But now remember that we just proved that this is a kite in the first one. So we can actually use properties of a kite. And one of the properties of a kite is that the long diagonal, right, cuts the whole thing in half. So if that angle is 30, that angle also has to be 30 because of diagonal of kite. Right, so that's what I did. I found that C1 is 30 and therefore they will actually both be 30. So that whole angle ACB is 60. Any questions on that? Did anyone do it in a different way, finding ACB? Sure, there must have been other ways. You could maybe have used opposite angles of a cyclic quad. That's fine, yeah. All right, then for the last one there, they asked you to find AQB, which is that one over there. So I, again, used the diagonal of a kite thing. So I found that Q1 was 60 because of angle, sum, and triangle of this small, like middle one almost, that one that's there. Because we had 60 and I can't remember now how I calculated. I had that 60 from somewhere else, I think. I can't remember now. All right, but that angle was 60 because of angle, sum, and triangle. And then again, because that is basically a symmetry line, that diagonal there of the kite, it cuts the whole thing in half. So that one will also be 60. So that whole angle is 120. But you also could have used opposite angles of a cyclic quad if you had P1. Which I hadn't calculated it by then, but you could calculate P1, then that whole angle is 60, meaning that the opposite angle of the cyclic quad must be 120. That also would have worked. Any other suggestions for finding AQB? It was a bit confusing because you had so many angles and so many of them were the same as well. So there was a lot going on. There were lots of 30-degree angles, a lot of 60-degree angles. So there would have been lots of different ways of finding it. Then this last one was interesting, and we haven't really done an example like this before. They asked you to prove that APBC, which is now this whole shape, right? They asked you to prove that this is a rhombus. Now remember that a rhombus is basically a parallelogram that has all four sides equal, all right? So I suppose we haven't actually proven that this is a parallelogram, so we should actually write that down first. Do you guys remember in grade 10 last year? I don't know if it was under lockdown or not, now I'm not sure. You did Euclidean geometry with quads only, and then you did 4 ways of proving that a quad is a parallelogram. You guys remember that? There were 4 ways of proving it. The first one was showing that both pairs of opposite sides are parallel, or you could show both pairs of opposite sides are equal, or you could show that one pair of opposite sides are parallel and equal, just one pair, or you could show that opposite angles are equal. All right, so there are lots of different ways of showing that something is a quad. Because we have all of that information, it's probably easiest to show that all the opposite, well, both pairs of opposite angles are equal, right? Because that's 60 and that's 60. And then this is 120 and that's 120. Okay, so we actually have to write that down first. So for 8.4, let me just fill that in. Yeah.
Well, we used to know stuff like this for the tests.
Yeah, you did. So yesterday, we used to ask me if I could find a list of all the properties, and I actually haven't been able to do that, but I will. Okay, angle P is equal to C and angle, I'm just going to write PAC is equal to PBC. Therefore, APBC is a parallelogram. Yes, you do actually have to say that first, and then you have to prove that it's a parallelogram with all four sides equal. Oh, we need to put this in here as well. Both is opposite angles equal. All right, 8.4 here, because that's actually where it starts. Okay, so now we know that it's a parallelogram. Now we need to prove that all four sides are equal to each other. Now I'm just going to go up to the picture quickly. We already know that these two sides are equal. Okay, I filled them in at the beginning. It was because they are two tangents that come from a common point. So now we need to prove that these other sides are also equal to those two sides. All right, so the way that I did it was I showed that AP is equal to AC. Do we notice that they lie, if we're looking at that triangle, that those two angles are 30 degrees, right? So it's an isosceles triangle there. So AP will be equal to AC because of sides opposite equal angles in this triangle, all right? So there we can put our two lines over there. So now we have that 3 of the 4 sides are equal. Now we still need to prove that this side is equal to, we only have to prove that it's equal to one of the other 3 because the other 3 are already equal. So I did the same thing in that bottom triangle. All right, again, we had 30 and 30. So this again is an isosceles triangle. So because of sides opposite equal angles, BP is equal to BC. Therefore, all 4 of them are equal. All right, so see how I wrote it down? I said that APC is equal to C1. Those are the first 2 top 30-degree angles. Therefore, AP is equal to AC because of sides opposite equal angles. So that was in the top triangle. Okay, I'm just going to write here. This was in triangle APC, which you don't have to add, but just maybe if you're looking over this again, that was what we were looking at there. Then in the bottom triangle, P1 and C2, they were also both equal to 30 degrees. So the opposite sides are equal again. Because of sides opposite equal angles, this was now in that bottom triangle. Triangle BPC. You didn't really have to write this down, but I just rewrote that AC was also equal to BC. And that was from 8.1. We used that reason there already. So therefore, we have that it's a rhombus because all 4 of the sides, we've actually proven that they are equal. Yes.
We also use
to show that they're parallel. So that would have worked for showing that it's a palm. But you also have to show that the angles are equal, of the sides are equal. I mean, all 4 of them, because that's the property that takes it from only being a parallelogram to also being a rhombus. Okay, so this one was tricky, guys. But it's a nice question. I'm glad that we have it. Please make sure that you copy it down, just in case. I hope it does make sense as well. All right. And then we will just quickly mark number 9, which wasn't as bad, not as bad, not as long as number 8. And I didn't actually draw this picture. Okay, guys, I will post these answers again with today's video link as well. So if you're not done, you can go check there. Let's just quickly look at number 9. And this was all in terms of x. So they told us that that angle there at S is equal to x. They gave us some more information here. And they said that PR is a tangent. So remember, they have to tell you that a line is a tangent in order for you to use tan chord theorem and all that stuff. So they did tell us that this is a tangent. RO intersects QS at T. Okay, that's fine. VQ is parallel to OR. They did draw that in on the picture, and angle S is X. Now for 9.1, they're saying write down with reasons 3 other angles equal to X. The first one that I saw, I think, was Q4. Q4, tan chord theorem. Right, Q4 is an angle between the tangent and chord QV. So it should be equal to the angle subtended by QV on the other side of the of the chord, sorry. Right, tan chord. So I said that Q4 is equal to X. Then I said, after that, I said that R is also equal to X. Do we see that F shape? It took me a while to see that F shape, I'm not going to lie to you. Right, that F shape over there. So angle R is also equal to X because of corresponding angles, because these two lines are parallel, right? Okay. O2, is it? Yes, alternate angles. Yes, there's a Z shape there. Thank you. So O2 is X. Is that what you said earlier, Nina? I thought you said Q2. Q2, yes, Q2 as well. I think that's actually what I wrote down, but O2 also would have worked. Okay, guys, do we see? Oh, actually not. Sorry, actually not. My bad also, sorry. Because it's that outer one, right? Yes, it's supposed to be the inner one. Sorry about that. Q2, because of angles opposite equal sides. Yes. There we go. Q2. Yes. So this is like the back of the F, and then those are the 2 lines. Okay, so those are the 3 angles, guys. Let's see. I wrote them down. Oh, sorry. Q2 is equal to X because of angles opposite equal sides and radii. Then I said Q4 is equal to X because of tan chord theorem, and angle R is equal to X because of that F shape corresponding angles. Okay, then 9.2, prove that Qrso is a cyclic quad. Now, this was an interesting question. You had to work with angles in same segment, which I think we did an example on a while ago. So they're saying Qrso. All right, now obviously RS hasn't been drawn in, so we need to visualize that, or you can draw it in using a pencil, right? But we're going to have a line over there. This is the quad that they're asking us about. Now, guys, we have that is X and that is X. All right, so that means that QO can be a chord of a circle subtending 2 equal angles at the circumference, right? That's the third way of proving that a quad is cyclic. So I think we wrote it down somewhere. It's somewhere in my notes. I can't remember if it was with you guys or with the other group. All right, but it will be in the video. So I'm just going to say again, these are the 4 points. Hey, Q, R, S, and O. So in order to prove that it's a cyclic quad, we need to prove that those 4 points can lie on the circumference of a circle. Obviously, a circle that hasn't been drawn. Right now, if Q and O, if those 2 points lie on the circumference of a circle, then QO will be a chord. Does that make sense? Right? Because a chord is a line going from one point on the circumference to another point on the circumference. All right. Now, do we notice that QO is subtending 2 equal angles? Right? We have an X there and an X there. So the one angle is at point R and the other angle is at point S. Now, guys, the only way for those 2 angles to be equal, for a chord to subtend equal angles, is if both of those angles also lie at the circumference of a circle, right? Which means that angle, or point R, sorry, and point S also have to lie on the circumference of that circle. All right, so that is the more difficult way of proving that a quad is cyclic. Oh, sorry, sure. So angle S is equal to R. We proved that over here. All right, we proved that they're both equal to X. Therefore, QRSO is a cyclic quad. And that is the reason, guys. Converse angles in same segment. Okay, there are three ways of proving that a quad is cyclic. Opposite angles of a cyclic quad, exterior angle of cyclic quad, and then angles in same segment. Those are the three. Yes, Nina?
So if we had one R,
Yeah, then you wouldn't have been able to do this one, yeah. Okay, any questions on that one, guys, on 9.2? That is important that you are able to use that method of proving a cyclic quad. Yes, it's fine.
all the corresponding angles. Thing. So
Yeah.
is O2 and 3 equal
O2 and 3 will be equal to V2, yes.
and then as well as R equal.
Yeah. Because you essentially have two different F shapes being formed by the same parallel lines, yes. No problem. All right, then for 9.3, they said write down with reasons the size of PQS in terms of X. So if we go back to the diagram, the size of PQS is now this whole angle. PQS is that angle there. Right, so they want that angle in terms of X. Now guys, we already know that that part of the angle is X. Now what is this angle going to be? Q2 and 3 is going to be 90 degrees, hey, because it's subtended by the diameter. Okay, so VQS or SQV, doesn't matter how you want to write that. Or you could have said Q2 plus Q3. That angle there is actually a 90-degree angle. Let me write it in there. So that is X, this is 90. Right, so because VQS is 90 degrees, angle in semicircle, and that is X, the whole angle is 90 plus X. Okay, that was 9.3. VQS is 90 because of angle in semicircle, therefore the whole angle is 90 plus X. You don't need a reason for that, that's literally just adding two angles together. Then 9.2 was an interest, or 9.4, sorry, was an interesting question. They said, prove that T is the midpoint of QS. Now, if we go to the picture, T is this point over here. They're asking us to prove that this is the midpoint of this chord. Now, guys, I'm hoping that you can notice that OT is a line from the center, and it is meeting, it's cutting, intersecting, whatever word you want to use, this chord. Now, do we remember that very first theorem, theorem 1? A line from the center of a circle perpendicular to a chord bisects the chord, right? And if a line is bisecting a chord at point T, that means that T is the midpoint of this chord. Now, do we know whether this point or this line is perpendicular to the chord? We don't have any 90-degree angles there at the moment, right? But we know that that is 90. What shape do we have here? Okay. Oh, sorry, it's actually there. Sorry, I'm showing it wrong. There we have an F shape. Do we see that one? That is like the back of the shape, the back of the F, and then those are the two lines. So if that angle is 90, this angle is also 90 because of corresponding angles. Right? It's difficult to see that one there. All right, F shape. Yes. Yes, for T3, yeah, you could have. Yes, so you could have said that T3 is 90 because of co-interior angles. The C shape or the U, I suppose, in this case. We remember that co-interior angles add up to 180. So if that one is 90, this one has to be 90. So there we have it, guys. That line from the center is definitely perpendicular to the chord, meaning that it cuts the chord in half. All right, so T is the midpoint there. All right, so 9.4, I said that T2 is 90 because of corresponding angles, or you could have said T3 is 90 because of co-interior angles. That's maybe a bit easier to see actually. Therefore, OT is perpendicular to that chord to QS. Therefore, T is the midpoint of QS. Because of that reason, line from center perpendicular to chord. Okay, any questions, guys? We are going to keep practicing, all right, until Thursday. We just quickly need to go through a proof that you actually did last year already, but I want you to copy it down. Okay, so please make a heading. We are doing angle at center proof. Proof 3. It's the third one, yeah. Theorem 3. So it's proof number 3. You were supposed to do this one last year, angle at center. I think actually I'm going to write this one down with you guys today instead of just having you copy it down. So guys, like I said yesterday, the only time that you ever have to write down a proof is when they literally ask you to prove the theorem that states, and then they'll write the theorem out in words. Okay, otherwise you can just always use it. You don't have to prove it. It's literally only if they ask you to prove the theorem. Okay. So, sorry, I just got to catch up here quickly. We are doing the angle at center proof. Okay, I'm going to draw the picture quickly, the picture that they will give us. So just going to draw it here on the side. So that middle point there is the center of the circle. So if you didn't draw it using a compass, you just kind of need to kind of guess where the center would be. It doesn't have to be accurate. So we're basically drawing that like typical angle at center, angle at circumference kind of image. All right, that is what will be given, guys. They'll give you that picture. So let's call this A, B, and C, and the center is O. I'm just writing the theorem down again so that we at least know what we are trying to prove. I think you guys know it already, but I just want a proper note. Okay, guys, so everything that I've written in black is what they will give you. All right, so this will be given like in the question. All right, so they'll say, prove the theorem that states, and then they'll give you that whole thing. All right, the whole theorem, they'll write out. They will give you this picture, and the given part is also obviously given. All right, so it's basically what is on the picture. That is what they also write down. Sometimes they tell you what you're required to prove, but you do need to be able to fill this in. All right, so all this, the stuff that we must fill in, I'm going to do in blue so that you can see the difference there. Now, guys, if we're trying to prove this theorem, we're trying to prove the angle at center theorem. What does the angle at center theorem state? That angle AOB is going to be double the size of ACB. So that is what we are required to prove. AOB is equal to 2 times ACB. You don't need that time symbol there. You can just say 2 ACB. All right, that is what we're going to have to prove. We know that, all right, because we have been working with the theorem, but when we are proving a theorem, we are actually proving what we've been working with. So it might be a bit confusing. But again, guys, you only do this if they're asking for the proof, okay? Otherwise, you can just use it straight away. Now, the construction is something that you need to remember, right? You need to memorize the construction. We're going to write it down and we're going to draw it in on the picture. Okay, so what you're going to do is you're going to draw a dotted line connecting CO and just let it go past O as well. All right, so you'll see now when I do mine. So I'm drawing in this dotted line and I'm extending it. And the point that I stop at, I'm just going to call point D. So the construction, what did we do now? We joined CO, so join CO and produce, which just means lengthen or extend. I suppose you can use the word extend if you want, and produce to D. All right, so we are joining CO and we're making it longer, and where we stop, we have point D. Guys, just let point D still be inside the circle, okay? Don't extend it all the way out. Okay, now this proof is a bit more complicated than the two that were done yesterday, in the sense that we now need to introduce some variables to work with. Okay, it's going to be easier if we do it that way. So what we're going to do is, I'm going to write it all down, but I'm going to say that this angle is X and that angle is Y. All right, sorry, that's quite small, but just draw an X there and a Y over there. So we are going to write it all down now. I just want to explain it quickly. All right, we're going to say let this angle equal X and that angle Y. Now, guys, what kind of triangle do I have there? Isosceles triangle, hey? That is a radius, that's a radius. So if that angle is X, this angle is also going to be X. We are going to write it all down now. And the second triangle there, isn't that also isosceles? Right? So if that is Y, then this angle is also Y. Now, if we're looking at the first triangle there, do we agree that angle DOA is an exterior angle of this triangle? DOA, that angle there, because it's a side of the triangle that's been lengthened, right? So angle DOA is an exterior angle of this triangle. And how do we find the exterior angle of a triangle? It's always equal to the sum of the opposite interior angles. So this exterior angle is going to be X plus X. So that exterior angle is going to be 2X. Again, we're going to write it all down now. If we're looking at the top triangle, angle DOB is an exterior angle of this triangle. Remember how do you create an exterior angle? By lengthening a side of the triangle, and then the outer angle is an exterior angle. So this exterior angle is going to be equal to the sum of the opposite interior angles. So Y plus Y, so 2Y. Now isn't 2X plus 2Y double X plus Y? Yes, all right, and that's what we have to prove. We have to prove that this angle, which is 2X plus 2Y, is double this angle, which is X plus Y. All right, so that is the proof. That's what we're going to do. Let's write that all down. We're going to say let ACO equal X and BCO equal Y. So that's also something that you have to remember for this one. Okay, in the previous two proofs, we didn't have to introduce any variables. For this one, we have to introduce variables. It's just easier that way. Then we said that angle A is also equal to X and angle B is also equal to Y. I'm writing it in one line because we're using the same reasoning for it. The reasons there, or yeah, reasons, angles opposite equal sides and radii. Okay, that's how I knew that those two triangles were isosceles. Therefore, angle DOA is equal to 2x and angle DOB is equal to 2y. Again, because we're using the exact same reasoning, I'm writing it all in one line. Exterior angle of triangle now I'm just going to wrap it up by saying that AOB is then 2x plus 2y, that whole angle at the center, right? 2x plus 2y. And just to show nicely that it is double the one at the circumference, let's take out that 2 as a common factor and let's just write it like that. Right? Because ACB was just x plus y. Okay, so we have 2 times ACB. So now we can do that. 2 times ACB. And there we are done with our proof. Okay, there we have proven that AOB is 2 times ACB. Okay, does that make sense, guys? All right, that is it for that proof. Any questions? All right, I am going to give you some more questions just to do on your own now. Some practice questions. Have you guys done anything from exercise 7? Come on, Tay, you've done a few questions from the revision exercise, but I don't think from 7. Okay, so you are going to do for tomorrow, we'll mark it in class tomorrow, exercise 7 on page 209. I want you to do number, let's say number 2, which is working with values in those angles. And then number 5. Yes, sure. So guys, you have 15 minutes left. Please start working on that now. Numbers 2 and 5. Yeah, sure.